Hi, my name is Raili Jenkins, and today I'm going to be talking about conductors in an electric field. First of all, what is a conductor? A conductor is a material that allows free charge to move within it. The electrical forces around the conductor allow free charges to move in it until it reaches static equilibrium. Then after that point, the leftover charges will go to the outside of the conductor. Some common examples of materials are aluminum, brass, copper, and iron. And notice that these are all metals and metalloids. So you should already know what an electric field is, but I thought it'd be a good idea to do a quick reminder. So here's your brief reminder of what an electric field is. It is an electric force per unit charge. Electric fields are drawn in respect to a positive test charge. So the field lines move away from a positive charge and towards a negative charge, and this is depicted in the pictures below. The denser the field lines, the greater the electric field. Field lines in a conductor. Because an electric field is a vector, it has both parallel and perpendicular components. When calculating the force for both components, you will find that the parallel force is 0. This shows that the final field is perpendicular to the surface of the conductor. The picture depicted on the right shows this. So you can see both components of the electric field, and when you calculate the parallel force, it equals 0. Therefore, the only component left is the perpendicular one. In static equilibrium, all the field lines going through a conductor will be perpendicular to the surface. The field lines used to be linear, however they are bent when a conductor is present in order for it to be perpendicular to the surface of the conductor. The conductor is polarized, with field lines ending on the negative side and starting on the positive side. There are no field lines going through the conductor, and as you can see in the picture, the field lines curve in towards the conductor on the negative side, and then come out the positive side, and there are no field lines in the middle. The excess positive charge in a conductor is expelled uniformly across the conductor. This leaves 0 charge inside and perpendicular field lines. On the outside of the conductor, the electric field is very similar to that of a point charge, where the field lines move away from the positive point charge, and the picture to the right shows this. Non-spherical conductors. Non-spherical conductors have a greater concentration of charge at the points. This creates a large electric field at that point that can exert a force big enough to transfer charge. While these charges repel, the forces between the charges have direction, not allowing them to go anywhere else. The radius of this area is small, therefore more charge is required to exert the force. And I like to think of it as, because the area is small, charges kind of get trapped in there, creating the higher density of electric field. Now we are going to talk about some real-life applications of conductors in electric fields. Our first example are capacitors. A capacitor is made up of 2 electrical conductors. There is an electric field going between the 2 conductors that allow them to store energy. The plates are oppositely charged, and that creates a potential difference, creating the electric field. If the 2 plates weren't conductors, then the whole system would not work. The next thing we are going to talk about is a Faraday cage. A Faraday cage is a cage made up of a metal conductor that can block an electric field. They protect whatever is inside of them from the electricity on the outside. The cage works the same way as all conductors. The cage is polarized and no field lines pass through it. This is how the cage is able to protect the inside. Some examples of a Faraday cage are the metal shell inside of a microwave, which protects the outside from the microwaves within, the metal compartment of a car or airplane, which protects the passengers from getting struck by lightning in a storm, or the protective gear for electricians, which protects them from getting electrocuted on their job. We are now going to go over 3 practice questions, and the first question is, at what part of this conductor would you find the greatest concentration of field lines? And feel free to pause this question to give you time to think about it. Now that you've had time to think about it, let's go over the answer. The greatest concentration of field lines would be at point B. This is because it is the pointiest part of the conductor, so the charges get trapped there, and therefore there's a high density of charge. Practice question number 2. What is the purpose of a lightning rod and how does it work? And once again, go ahead and pause this to think about the question. Alright, here's answer number 2. The purpose of a lightning rod is to help protect a building from being struck by lightning by providing a low resistance path to the ground. The rod on the roof is connected to a rod buried in the ground. A lot of people like to think that the rod is simply just attractive to the lightning because it's metal. However, this isn't completely true. It's because the rod can provide that lowest resistance path that the lightning is most likely to strike there. Alright, here's our last question. Why are metals such good conductors, and why don't field lines move through them? Go ahead and pause to think about it. Alright, here's answer 3. Metals are such great conductors because of their chemical properties. Each atom in a piece of metal shares electrons, creating a sea of floating electrons. This gives the electrons a lot of freedom of movement. This is essential for making a good conductor. Once you put a conductor in an electric field, the electrons will arrange themselves in a way to cancel all the field lines inside of a conductor. This keeps the charges at their lowest possible potential. This is why the field lines are perpendicular to the surface of the conductor. Alright, that's all I have. Thank you for listening to me talk about conductors in an electric field.